Hey, hello, how are we doing today? So, today we are going to look at this um, case study. Can AI really do math? Case study in proofs. So, first of all, what is a proof, right? Well, a mathematical proof is a rigorous logical argument that demonstrates a mathematical statement is undeniably true for all possible cases, not just some. Um, AI can write full math proofs instantly, but the question is, does it understand the math, right? So we're going to basically look at a human proof and an AI written proof and compare them. First, so let's I want to introduce some terms first so we can so you can kind of get a better understanding of like some terms that are in the proof, you know? So first of all, what is a limit, right? A limit is what a function is approaching. So basically, if you think back to your high school days, your algebra days, if you have any recollection of them, of what you learned in earlier math classes in life, um, you have a function, f of x. X is the input, f of x is the output. So as x is approaching a, some value along the x-axis, in most cases, we use infinity. F of x, what value is the function f of x approaching, which is sorry, which is L, right? So as x is approaching a value, f of x is approaching a value also. Usually we care about the behavior near a point. So usually we use x is approaching infinity to kind of know the long-term behavior of a function, right? As x goes to infinity, what is f of x approaching, right? So what is f of x approaching long term, right? So you can think of it approaching a number without actually touching it. We're approaching a number. We're not touching it. We're getting infinitely close to it. And how do we study limits in mathematics? Well, we use sequences. What is a sequence? Well, a sequence is just a list of numbers, right? You see some examples here. A sub n, right? A sub n here is sequence n squared. So they're numbers that follow certain patterns. So n for every term you square it. 1 squared is 1, 2 squared is 2, 3 squared is 3, go on and goes on to infinity. And here's another one, b sub n, where it's 1 over n, 1 over 1, 1 over 2, 1 over 3, 1 over 4. And then here, same thing, 2 times n plus 1 pi, right? So it's just a list of numbers that follow a certain pattern, right? So as a sequence approaches some point, which we call x naught, we look at what happens to the sequence of that function, right? Um, and that kind of tells us the limit, that is the definition of the limit of the function, right? And the Cauchy sequence is a special kind of sequence that we're going to be using in the proof that basically is a convergence sequence, right? Terms get closer and closer and it settles down at a certain point. So as the sequence goes on to infinity, it converges, meaning it approaches a certain point. We see that here, b sub n, 1 over n, right? As this number gets larger, this approaches 0. As n goes to infinity, this gets smaller and smaller and smaller, and it approaches 0. So this is convergent, right? However, n squared is divergent. It doesn't approach a number, right? Because as this increases, this gets larger and larger to infinity. So it's divergent, right? Um, so a Cauchy sequence is convergent. It's a sequence where it it kind of it converges or it approaches a number as it goes to infinity. What is continuity? Well, a function is continuous if there are no jumps, breaks, or holes in the graph, meaning you can draw it without picking up a pen. So for example, here, you can draw it. It's one continuous line, versus here, there is a jump, right? In terms of a limit, though, the value of the function matches the limit you're approaching on both sides. So here, for example, if you pick this point, the limit here from the left side, which is approaching, is that point, and the limit from the right, the value you're approaching, is also that point. And the function, the value of the function matches the limits on both sides. So that's continuity, right? The value of the function matches the limit. Um, okay. And there's a special case of uniform continuity, which will be in the proof, which basically means small changes in x imply small changes in f of x, meaning it behaves nicely. It's uniformly continuous throughout, right? There's no wild behavior, right? And this works the same everywhere. Okay, what is an accumulation point? Well, an accumulation point is a point you can get arbitrarily close to, even if you never actually reach it. Meaning, and there are always points near that point. So for example, 1.9, 1.99, 1.999, you're getting closer and closer to 2. This makes 2 an accumulation point, right? And that is basically meaning that you can approach, it's a point that you can approach, which is um, part of the proof as well. Okay, so this is the theorem that we're going to be proving. And the theorem states that f from d to r is a function from d to r. D is the domain where your inputs are coming in, and R is the codomain where your outputs are, the region where your outputs are, right? Be uniformly continuous. Then if x sub naught is an accumulation point of D, f has a limit at x naught sub naught, x naught. So basically this theorem is saying, to put in simpler terms, if f is uniformly continuous, and this point, x naught, is a point that you can approach, then the function f of x approaches a value at near this point, right? The function approaches a value as x approaches this point, okay? Basically, if the function has nice behavior everywhere, the function also has nice behavior, continuous behavior at that point. Okay, so this is the human proof, the proof that I constructed. And basically, it looks a little bit, I know it looks a little crazy and a little bit daunting, but it's not. And I'll walk you through it. I'm not going to walk you through everything. Obviously, there's a lot of intricate things that we learn in real analysis, right? That you don't, you, that's very difficult to grasp, but I'll break it down for you in a simpler way. Um, Basically, you want to show that as x approaches a point, the values of f of x also approach a point, a single number, aka the limit exists. So basically, in the proof, we took a sequence in the domain D that approaches a point, and the point we call is x naught, and we look at the outputs of the function, right? So instead of proving these outputs have a limit directly, we show that they form a Cauchy sequence, which is a sequence that the sequence of those values converge. And uniform continuity is kind of the key idea in this proof because it guarantees that whenever the outputs are close, the inputs are close, the outputs are also going to be close. So since that's the sequence of the x's approaching a value, approach a value, the sequence of the x sub n is Cauchy. So it converges, and uniform continuity forces the sequence for the values of the function to converge also. So therefore, that sequence is Cauchy, and it converges, which means that f of x approaches a single value as x approaches x sub naught, which is precisely what we wanted to show here. So we use the definition of Cauchy sequence, we use the Cauchy sequence and applied uniform continuity to it to prove that as f of x, that f of x approaches a single value as x approaches x naught. So therefore, a limit exists at x naught. Now, this is the AI proof. As we can see in the human proof, every step is justified and nothing is assumed without a reason. It's logically sound. Now, in the AI proof, it uses two sequences instead of one, and it shows that outputs get close. It concludes that a limit exists, or it comes to the same conclusion. However, and at first glance, it looks completely correct, right? However, we will see that there are some gaps in the logic. So what the AI proof gets right, it uses correct definitions. The logical structure looks solid and it reaches the right conclusion, which is why AI is convincing, right? If you look at this proof, you look at it and say, well, it looks correct, right? However, it's the subtleties, the small subtleties that make the difference. What AI gets wrong. Well, it skips key justification and assumes a theory without stating it. It doesn't explain why the limit exists, and it shows how sequences get close, right? So basically, it shows how sequences get close, but doesn't fully justify that this guarantees a sequence. It kind of just goes to the Cauchy sequence and kind of just like it skips a step. It doesn't clearly, rationally, kind of logically come up with the point that this guarantees a limit, right? It just shows the sequences get close and therefore this and this and this, but it doesn't fully justify that this guarantees a limit. So it does it. It is a valid approach, but it's missing one key line of explanation that connects two things together. So it's missing a bit. It's missing rigor, which means it's missing proof, right? It's not a complete proof. It's still a good proof. Like you can give it a B plus or an A minus, right? But it's still missing a tiny bit of rigor. Why this matters? Well, it matters because math requires precision, right? Without precision, and without justifying every single step logically, you cannot come to the conclusion that something is true for all cases, right? Gaps matter. Almost correct is not correct. You need to be able to prove it for all cases, for all circumstances, and back that up by clearly stating things with clear reason. If you miss a certain statement or a certain justification, it's not a full proof, right? You can't just sound right, you must be right. So what's the final takeaway of all this? Well, the final takeaway is that AI is good at mimicking structure, but it struggles with deep reasoning, right? That human understanding that we can explain why something is true, right? That deep reasoning that AI still lacks, right? That kind of makes a proof fully rigorous or fully complete. So the conclusion is that AI can imitate a proof, but it doesn't always understand it. So we still see that there are major limitations in AI when it comes to proof writing, although AI can still generate a really good proof. And that is my presentation. Thank you for listening.